So here we are given that if we take the scalar dot product between the vector r and the differential dr vector, if this value is equals to 0, this would mean that the magnitude of the vector r is a constant. So let's try to prove this. So here we will start with the idea that when we have a vector r and take its dot product with itself, so this gives us magnitude of the vector r squared, or simply r squared. It will mean exactly the same thing. Now let's take the differential dr vector dotted with r vector. Now what we'll do, we'll use the product rule. So this should give us d, or we'll call this the first vector function, and this is the second vector function. So we'll take the differential of the first vector function. So we have dr vector, so this will be dotted to the second function, which is simply r vector, plus now we'll take the first function r vector and dot it with the differential second function, so dr vector. Now we know that the scalar dot product commute, so that means dr vector dotted with r vector is the same as r vector dotted with dr vector. So this will become equals to 2 times r vector dotted with dr vector. So this is d r vector dot r vector, which is simply dr squared. So we have obtained the result that dr squared is equals to 2 times r vector dot dr vector. And it's given that r vector dot dr vector, that's equals to 0. So we can say that dr squared, so that's equals to 0. So this is given, r vector dot dr vector is 0. Now when we have the differential dr squared equals to 0, that would only mean that r squared must be a constant. If r squared is a constant, that would also mean that this r squared is simply the magnitude of vector r squared, which is a constant, or simply magnitude of r is a constant. So here we have shown that if we have the condition that the dot product between vector r with its differential dr vector, that's 0, that it would mean that the magnitude of the vector r must be a constant.